All right, welcome to a bit of a nerdy math computer science mini lesson here. This one's on a topic called round off error. Round off error is when two numbers are being added, multiplied, divided, whatever, and the answer you get is not the answer you expect. And this occurs because the computer is storing the numbers in binary. And believe it or not, there's some numbers that if you try to put them into binary, you just can't get to be exactly equal to a binary representation. So what happens is you get something called round off error. The number is very close, but not exact to what you're looking for. Example, 1 plus this number, well, we know it should be 1 plus a little bit. So I'm going to print it out. You should expect 1.00000 and eventually the 1. Then I'm going to check, is C equal to 1? Well, we know it's not. But if it is, C does equal 1 should print out. So this is the output when this is run. And if you don't believe me here, we'll just run it again. C is 1. So first of all, that's wrong. And then it says C equals 1. That's not right either. And so this is a little prime example of round off error. This particular number, not good with doubles. Implications, you could have engineering problems where little tiny errors keep adding up and adding up and adding up to make a big error. You could be sending a satellite into space, it's going around planets for 25 years, all the gravity and all those calculations have to be exactly on, but little by little you're going away from the real answer, and eventually that causes a big problem. Okay, so that's just one simple example. Now, how bad can this actually be? I'm going to skip example 2, and I'm going to go to this method, find bad numbers. What this one is going to do, those good at math here should clue into what this should be, but I'm going to take x and y, keep changing the numbers around, and I'm going to say x divided by y, give me an answer. Then I'm going to take b and say it's y divided by x. Now, you know those are inverse. So if I multiply a times b, mathematically, you know you should get a 1. Guaranteed. But what I'm going to do a quick check here is, if I don't get a 1, which any math teacher would tell you, that's never going to happen. I'm going to print out that x, that y, and what the value of c is, just to see what the computer thinks it is. Okay, and this is a glaring example of why the math round off error and loss of precision is a big issue, because you're going to see lots of numbers just in these tiny ranges don't actually equal 1. Now, unfortunately, I didn't do a print line, so it's all sideways. But you can see here, I have when x is 3 and y is 73, c equals that number. Okay, when it's 3 and it's 76, c is that number. And this goes on and on and on. There's lots of bad numbers in that small range. And so which numbers it occurs with is actually quite unpredictable and actually depends on the computer. So you could run this on your computer and you may get a different set of numbers that this occurs with, believe it or not. What else can we tell you here? So that's just another example that it does in fact happen. The last thing we'll show you here is, let's say you're doing these kind of calculations in your program and you actually want to know, are they equal? But you also understand that even when it's supposed to be equal, it might not be equal. What can you do? Well, what they do, typically, one solution is you write a method, and I called mine really equal, and I give two numbers. And the purpose of this method is to tell me, are these numbers equal? But what I set up here is I set up what they call a tolerance. And if you actually just follow the code on your own afterwards, you'll see that I've set this tolerance of 0.000001. And if you read this code, you'll see if the numbers are within that range of each other, the method will send back true. The numbers are equal. So it's a bit deceiving. The numbers might not actually be equal, but if they're pretty darn close to equal, it's going to send us back true. And of course you could change this tolerance to make it closer to what you need if you need really accurate. In example 2 here, you'll see I use it. 1 plus a number, I add them up, and then I'm asking, are they really equal? If they are really equal, which really means close enough, then it prints out really equal, says equal. If not, it'll say not equal. Now, does it work? Example 2. And you'll see there, really equal says that the two numbers are equal, the 1 and the C. And so it's not perfect, but it sort of takes that into account. So if you ever have a program where you're dividing doubles and doing weird stuff and you think this is not working correctly, you have to consider that round off error might be happening to you. So it's a real concern in programming. I have one more method there. It's just a limit test. Just to give you a brief on it here, you start at 1, divide it in half, add it on. Go back, divide it in half, add it on. And you keep repeating. So what's supposed to happen here? It's supposed to be something like 1 plus half, plus a quarter, plus an eighth, plus, and it keeps going and going and going. Limit test. We'll see what it actually prints out here. And you can check online and see what it's supposed to actually print out. So it prints out that. Now that number is a special number. You can go check online and you're going to find out something. You probably can guess the answer, whether that's the real number or not the real number, and what the real number is supposed to be. So you can do a little Google search on that one. That's it. That's round off error. That's one way to take care of it. And I guess another way to take care of it, people have actually written classes specifically when